Hi everyone, so now I'm going to show you how to calculate the independent samples t-test, okay? This is the last video for chapter 5. So independent samples t-test is where you have an independent variable that is discrete, just like with analysis of variance. The key thing is that it can only have two groups. Okay, you cannot have more than two groups. The dependent variable is continuous, just like with the analysis of variance. Okay, so you can use it in the same situations you use analysis of variance if you only have two groups. If you have 3 or more groups, you have to use analysis of variance. Now, why would you use independent sample t-test? Well, it's a lot easier and faster to calculate than ANOVA, okay? So it's mathematically equivalent to ANOVA, okay? It's not exactly equal, so here's the relationship. So t squared equals f. All right, so you're going to see later here, I'm going to calculate our t value, and we're going to use the same data I used in that complete example I did for ANOVA. And we're going to check, and we're going to see if we square our t, does it equal the f I calculated previously, okay? So it's the same basic idea. We're going to get a ratio of between group variability over within group variability, but we're going to do it just a little bit differently because we're going to be using, instead of variance, we're going to be using standard deviation, standard error, and instead of our between group mean squares, we're just going to take the difference between the means. And so it's a little bit different mathematically in the calculations, but it's going to always give you the same decision. So you won't get one decision with ANOVA and another decision with t-test. All right, so we're going to, just to remind you, we're going to use the same data, the classical music versus no music, and the quiz scores. So the same exact data that we used in the complete example for ANOVA. Okay. And so we're going to start out with our hypotheses. So mu1 equals mu2. So you write it just the same as you would for ANOVA. Just keep in mind it's only going to have two groups. For the alternative hypothesis, we're going to write mu1 does not equal mu2. We're going to do this for the t-test because, again, you're only going to have two groups. So you can always just write mu1 does not equal mu2. All right, so now we're going to do degrees of freedom and our decision rule. Okay, so we only have one measure of degrees of freedom for t-test. And so it's called degrees of freedom for the difference. And this is because we're looking at the difference between our means, okay? And the formula for this is n1 minus 1 plus n2 minus 1. This formula will work if you have different sample sizes in your groups. We just have the same sample size in both groups. We have 6 people in each group. So it's going to equal 5 plus 5, which equals 10. Okay. And there is a special table for the t-table to find our critical value. So we use table A3. It's on page 534 in your book. And let me just show it to you. I took a picture of it here a second ago. Okay, so this is what the table looks like in your book on page 534. And you can see that the title says critical values of the t distribution. Okay, so you want to make sure it says that. And this table is a lot simpler to use because we're just looking up one critical value. So you can see it gives degrees of freedom down the first column. The second column gives the critical value for alpha equals 0.05, and then the third column gives the critical value for alpha equals 0.01. So our degrees of freedom is 10, and so we're going to use alpha equals 0.05, so we're going to use 2.23. I'm just going to a little bit there. So for 10, it's 2.23, okay? And then we're going to go back to our notes, okay? So our T alpha, our critical value, is 2.23, okay? Now, we do write our decision rule a little bit differently for the t-test, and this is because it's possible to get a negative t-value, okay? And that is okay. With F, because we're dealing with variances and everything is squared, it has to be positive. But with t, we're not looking at squared values, so it's possible to get a negative value. And so we have to take that into consideration. And so what we say in our decision rule is that we are going to disregard the sign when we're making our decision. So we're not going to completely ignore the sign altogether, but just while we're making our decision, we ignore the sign, and then after that, we will take the sign into consideration. Okay? All right, so here's how we write the decision rule. If the obtained value of t, disregarding sign, equals or exceeds our t critical, our t alpha, equals 2.23, we're going to reject the null hypothesis otherwise fail to reject the null hypothesis. Okay, so that's our decision rule. So the key difference, besides talking about t instead of f, is, whoops, I forgot the word sign. Disregarding sign. Okay, so that's the key thing. So if the obtained value of t, disregarding sign, equals or exceeds t alpha equals 2.23, reject the null hypothesis, otherwise fail to reject the null hypothesis. So the key difference is this disregarding sign part, and of course that we're talking about a t rather than an f, okay? So now we're going to actually calculate our t value. Okay, so the first step in calculating t is, well, I'll write the basic formula here. So t is going to equal y bar 1 minus y bar 2 divided by what's called sigma hat of the difference. Okay, the sigma hat is our measure of within group variability. It's called the standard error of the difference between the two means. Okay, and the top part, y bar 1 minus y bar 2, is going to be our mean for group 1, classical music, minus our mean for group 2, which is no music. Okay, so the difference between the sample means, that is our between group variability. The standard error of the difference that is going to be our measure of within group variability. Okay, and you're going to see it takes into account the standard deviations. All right, so I'm going to go ahead and calculate the standard error of the difference first, because that is the most complicated part. The formula for that is the variance for group 1 over n plus the variance of group 2 over n, and we're going to take the standard deviation of that. Okay. We calculated the variances in the last video when I did the test for homogeneity of variance, so we're just going to use those variances. But you would calculate a variance the same way you would for any time you're doing variance for a single group. So those variances that we calculated in the last video are 3.5 for group 1 over 6, and for group 2 it was 0.57 over 6. Okay. And so you notice we're taking the square root, and so that's why this is a little more like standard deviation rather than variance. Okay. It does take into account the sample size, and that's why it's called standard error. So the fact that we're dividing by n, that's what is the reason why it's called a standard error rather than a standard deviation. If we were just taking square root, it would be more like standard deviation. Okay, so now we're going to divide 3.5 by 6, and we get 0.58. And 0.57 divided by 6 is 0.10. Then we combine those, so it's the square root of 0.68. And we take that square root and we get 0.82. Okay, and so now we're going to use that and plug that into our formula. So we're going to take our two means from our data. The mean for group 1 was 7.5, and the mean for no music was 8.17. We're going to plug those in, and then we're going to put our 0.82 here as our sigma hat of the difference. Okay. You're going to see this is how you can end up with a negative t-value, because our second mean is bigger than our first mean. And so this comes out to be negative 0.67 divided by 0.82. And we do our division and we get negative 0.82. Okay, so that's our t-value. All right, and I told you I would check, but I'm going to write our decision and conclusion first, and then we'll check. Okay, so to do our decision, we compare this negative 0.82 with our critical value. So our critical value is 2.23. Now remember, this is where we want to disregard the signs. So we ignore the negative while we make our decision. So 0.82 is less than 2.23. Okay, so because of that, our decision is going to be fail to reject the null hypothesis. And that's what we decided in our ANOVA with the same data. You're going to write the conclusion pretty much the same way, okay? The only thing that's going to change are the numbers at the end. Okay, so music condition did not have a significant effect on quiz scores. And then now this is the part that's different. So we did a t-test, not an f-test. We had 10 degrees of freedom. Okay. And our t-value, here we do put the negative. Our t-value was negative 0.82. And p was greater than 0.05. Okay, so this is still the alpha. And the rationale is the same idea here, right? So if we had rejected the null hypothesis, the probability that we would be wrong is greater than 0.05. That's why we failed to reject the null hypothesis. Okay. All right. Okay, so that's the conclusion. Now, if you had rejected the null hypothesis here, because we have two groups, you would want to write a more specific conclusion. So, if, let's say, if t had equaled, let's say, negative 5.82, okay, then 5.82 is greater than 2.23, okay, so we would reject the null hypothesis. And remember, I told you that if we have only two groups and we reject the null hypothesis, we would want to write a more specific conclusion. And so if we go up here and look at our t-value again, you can see that the mean for group 2, the no music, is higher than the mean for group 1 with classical music. So we would want to talk about that in our conclusion. Okay, so you would want to say something like people who studied without music had significantly higher quiz scores than people who studied listening to classical music. And you would have t with 10 degrees of freedom equals negative 5.82. P is less than 0.05. Okay, and so if we had actually gotten a t-value of negative 5.82 instead of what we actually got, our decision would have been to reject the null hypothesis because we ignore the sign when we make our decision. So remember, ignore the sign when you make the decision. Then you want to give a specific comparison of the two groups. Okay, and also remember the sign in your p value is going to change, because if we'd gotten this t-value of negative 5.82, then the probability that we would be making a mistake when rejecting the null hypothesis is less than 0.05. So that's why we decided to reject it. The risk of being wrong is very low. Okay? All right, so now let's go back and think about, so our actual t-value that we calculated was negative 0.82. The f value when we did our ANOVA in the last video was 0.66. Okay, and I told you at the beginning of this video that the relationship is that t squared should equal f. Okay, so let's see, negative 0.82 squared. When we square that, we get 0.67. Okay, so it's not exactly equal, but it's pretty close, right? That's only 1/100th of a percent off. Okay, so that's how that relationship works. So even if the t is negative, because you're squaring it, it's going to become positive, and then it should equal your f value. Okay, now you would only, it's very rare that people actually do both the t-test and the f-test on the same data, so typically you're not going to be checking this, but I just wanted you to see the mathematical relationship. Okay? All right, so that is the t-test, and that is the end of what we're going to be talking about for Chapter 5.